Let's look at a plane. Now, the equation of the plane goes something like this: ax plus by plus cz plus d equal to 0. But you might notice, if you remember two-dimensional geometry, ax plus by equal ax plus by plus c is equal to 0 is the equation of a line. Now here, because we have z direction, we include cz to get the equation of a plane. Now, when you do this, you might notice a thin line going, and you might wonder, this is not a plane. But if you rotate it a little bit, because we were looking at the plane edgewise, that is why it was looking like a line. Okay, now here, if I say the equation of the plane is x equal to 0, that means it doesn't matter what the value of y and z is, x is always 0. So let me make this disappear. So this is the YZ plane. So you look at any point, you take any point on this plane, x will be 0. Only YZ will have values. Okay, which means similarly y equal to 0 would also be a plane, and this would be called XZ plane. Naturally, z equal to 0 will give you another plane, that is XY plane. Because we already have a plane, actually from the beginning of this series of videos, we have this XY plane always shown, just so that we can orient, we can visualize the correct orientation. Okay, if we don't want that, we can ask it not to display it. Now if I display the planes, yes, so which means in a three-dimensional coordinate system you will have 8 quadrants, 4 on top and 4 on the bottom. Okay, so one of the equations, or one of the ways in which you can show the equation of a plane is ax plus by plus cz plus d equal to 0. Now let's look at another equation, right? Another way at arriving at this equation. For that, let me begin from the start, right? So let's say A1, B1, C1, A2, B2, C2, A3, B3, C3, A4, B4, C4. So basically we have 4 points, and we have already seen this in our previous session, right? Tetrahedron, and we said when the volume of the tetrahedron is 0, the points are coplanar. Remember that? So basically those 4 points lie on the same plane. Now there we were talking of specific points, right? Now if we make one of the points as an arbitrary point, so first let's get this ready. So we use row matrices, right? So A1, B1, C1, A2, B2, C2, A3, B3, C3, A4, B4, C4. Now I didn't actually have to create these points. I could have directly chosen, you started with this. But it's easier to visualize if we have these points. And if we connect these points, it's much more clearer. Anyhow, so now then we came out with the direction ratios with respect to one point. Okay, so we said L4, or let's say L1 minus L4, L2 minus L4, L3 minus L4. Yes. And these three row matrices, we combine them into a single 3 by 3 matrix. So L5, L6, L7 to get this. And then what we did was determinant of this M1 is the volume, and because of calculations it can be negative, we said absolute value of this, right? And divide by 6 gives us the volume. But remember, for the volume to be 0, that divide by 6 itself is just to get the volume, but the volume itself will become 0 if the determinant is 0. So when the determinant is 0, these lines are coplanar. That means they lie on the same plane. But since these are all specific points, we can only say that these 4 points are coplanar. But if we make one of these points as an arbitrary point, then we end up with a equation in x, y, and z. So let's take L1 as, instead of A1, B1, C1, let's say x, y, and z, and see what happens. So you see this now, because variables are there, it is not evaluating it. It can't evaluate it. It is not building the equation, but we know how to do it. Okay, and this is how it looks like. So determinant of this equal to 0. But remember, the determinant equal to 0 will give us the equation, because it's only when the determinant is 0 that these 4 points will occupy 0 volume when we connect these. Okay, so this is what is called as the equation of the plane passing through 3 points. Remember, one of the points we have taken it as arbitrary point, x, y, and z. Now, another type of equation is called the normal equation. No, sorry, intercept form of the equation. So here we have x by a plus y by b, y by b plus z by c is equal to 1. So again, if you notice, we have the intercepts are all 1. So this is 1, 1, 1, right? So A, B, C are the intercepts. A is the x-intercept, Y is the B is the y-intercept, and C is the z-intercept. If I change this, only the x-intercept will change, right? Okay. Accordingly, in the other two cases also, same thing will happen. So this is the intercept form of the equation. Now let's look at another type of equation of a plane, that is a normal form, right? So let's start from the beginning. Let's say we know the magnitude. So let's say the magnitude of the line perpendicular to the plane from the origin is, say, 3 is equal to 3. Okay, and the direction cosines also we know. So L is equal to, remember, cos will always be between -1 and 1. So let's say minus 0.34, and let's change this to -1 to 1, and step let it be 0.1, and this will be from 1 to 1. Okay, m is equal to, or it's faster to type it like this, -1 to 1, and step is 0.1, right? The only thing is this should be lm. Okay, slider -1, 1, 0.1, and this again should be n, because conventionally we say Lm and n are the direction cosines. So that's the reason why we are doing this. So let's move this a little bit. Okay, and let's see what happens. Okay, so now we have the perpendicular distance, we have the direction cosines, right? So, and let's say x, y, and z are the direction ratio of the normal to the plane. So Lx plus My plus Nz is equal to P. Yes. So we get the plane, equation of a plane. Now as we move the distance from the origin, perpendicular distance from the origin increases or decreases, right? Similarly, as I change the direction cosines, it will rotate depending on which direction cosine I am changing. So that is called the normal form of the equation. So that's it. Bye for